Hi everyone, it's Mrs. Meehan, and in this lesson I'm going to go over the momentum of a system of objects, and then a little bit later the concept of conservation of momentum. So if a system contains more than one object, the total momentum is the vector sum of the momenta of those objects. So vector sum just means it's taking into account the direction or the signs of those separate objects. So if we wrote this out algebraically, we have the momentum of our system, and that would be equal to the net momentum for each object in there. So for each object, you need to take into consideration each object's individual momentum, and then the sum of that will be the momentum of the total system. So let's say we had 3 or more objects, you would have to write it out as, okay, the momentum of the system will be equal to the momentum of object 1 plus the momentum of object 2 plus the momentum of object 3, etc. Now we also remember that according to the equation from the last lesson, that momentum is equal to the product of mass times velocity. So for each object here, that means for object 1, it's the mass times velocity of object 1 plus the mass times velocity of object 2 plus the mass times velocity of object 3 plus however many other objects are involved in this system. And by doing that, you would get the momentum of the system as a whole. So now that we have an equation to represent the momentum of a system, or the net momentum here, adding it all together, in order to determine total momentum of a system, there are a few steps that you want to follow. So let's take a look. One thing that you're going to want to consider is the direction. That's going to be positive. And traditionally, what we'll say is that, if it's going to be positive, then positive would be up or right or east and north, since those kind of correspond to up and right. So those would be your positive directions. Compared to negative, what we traditionally use would be the opposite. So down, left, south, and west. Those would traditionally be our negative directions. So, sorry, that should say negative. So just make sure that when you are deciding what the signs are, that you are assigning them correctly. So choose a direction considered to be positive. You would assign positive values to all the momenta in that direction. So the objects there, the momentum for each individual object, which ones are positive. Then you would assign negative values to the objects heading the opposite direction. So if we have momenta heading right, that would be positive. And then if you had another one heading left, that would be negative. Then you want to add that all up using the above equation here to get the total momentum of the system. So taking a look at a practice problem here, determine the momentum of a system of 2 objects. So we have M1 has a mass of 6 kilograms and a velocity of 13 meters per second toward the east. And M2 has a mass of 14 kilograms and a velocity of 7 meters per second toward the west. So taking a look here at the first step, we're going to let east be positive, since that is traditionally what we'll do. So we have east versus west here. So east would be the positive direction, and west would be the negative direction. And then also keep in mind our equation here. Our system consists of 2 objects. So the momentum of the system will be equal to the momentum of object 1 plus the momentum of object 2. So we've assigned what is positive. Now also consider breaking it down further into the values here, the variables for momentum for each object, and use subscripts to keep track. So remember, our overall equation for momentum is P equals mv. So you want to write that for each object. So for object 1, it's mass 1 times velocity 1. For object 2, we have mass 2 times velocity 2. Now on the left here, we have a summary of what has been given. So for object 1 is 6 kilograms, and it's going 13 meters per second. And since it's heading east, we've determined that is the positive direction. So it is positive 13 meters per second to indicate direction there. For object 2, we've assigned it a negative value for the velocity because it's heading west. That is the opposite direction of east. So it is assigned a negative value, and that is 14 kilograms in mass. So now you'll notice on the right here, we have our work continuing. So putting the numbers in, mass 1 and velocity 1 is 6 kilograms times 13 meters per second. For object 2, mass 2 and velocity 2, we have 14 kilograms times negative 7 meters per second. So what we end up with is 78 kilogram meters per second. Remember, that's the unit of momentum. So that is for object 1. That's the momentum of object 1 right there. And on the right, we have negative 98 kilogram meters per second. That's the momentum for object 2. And it's negative because we have the negative velocity there. When you add it all together, you end up with negative 20. So the momentum of the system, once you find the net momentum of both objects here, you end up with negative 20 kilogram meters per second. So you end up in the negative there because of the larger mass of object 2 would have a greater magnitude of momentum. It just works out that way. Plus you have the negative sign here in the velocity. Okay, let's try a couple practice problems. So determine the magnitude of the momentum of a system of 2 objects. M1 has a mass of 6 kilograms and a velocity of 20 meters per second north, and M2 has a mass of 3 kilograms and a velocity of 20 meters per second south. Okay, let's take a look here. Now, the correct answer here is 60 kilogram meters per second. So if you chose letter D, you were correct. And the direction is north because it is positive. So we know that we have the mass and velocity for each object here. And just like we previously worked out on the last slide, you have the net momentum here, the momentum of the entire system. For object 1, it's the 6 kilograms times 20 meters per second. And 20 meters per second is positive because it's north, and we'll consider north to be positive and south to be negative. So for object 2 here, it's 3 kilograms times negative 20 meters per second, negative because it's heading south. Add it all together, you end up with 60 kilogram meters per second. And you could either indicate that it's positive or it's obviously positive with how it's written. You could also state that the direction would be north because it's positive. Determine the momentum of a system of 2 objects. The first has a mass of 8 kilograms and a velocity of 8 meters per second to the east, while the second has a mass of 5 kilograms and a velocity of 15 meters per second to the west. So for this one, negative 11 kilogram meters per second to the west. Since it is negative, that would be westward. So if you chose the answer C, that is correct. So we know that the first object there has the mass of 8 kilograms, and it is in the positive direction because it is to the east. East would be positive. For object 2, it's heading west, and it's the opposite direction. So that would be negative 15 meters per second. You put it all together, and you end up with negative 11 kilogram meters per second west. Determine the momentum of a system of 3 objects. The first has a mass of 7 kilograms and a velocity of 23 meters per second north. The second has a mass of 9 kilograms and a velocity of 7 meters per second north. And the third has a mass of 5 kilograms and a velocity of 42 meters per second south. Okay, so keeping in mind our directions here and what would be negative and positive is the first step. So north would be considered positive. So two of those objects are heading north, the first two objects, 1 and 2. So they would be assigned the positive values here. Object 3 was heading south in the opposite direction. So that one is assigned a negative value for its velocity. Now remember, our equation is the momentum, the net momentum of all three objects. So once you put that all together, you have to find the momentum of each individual object and then add it together. You should end up with 14 kilogram meters per second north. Letter B. Now let's take a moment to go over conservation of momentum. So in the last unit, the energy unit, we talked about conservation of energy, how energy is neither created nor destroyed. And then the initial and the final energy of a closed system would be equal. The only way to change the amount of energy in a system is to perform work or apply a force from outside of that system. So we see a similar idea in the conservation of momentum. So conservation laws are some of the most powerful concepts in science. Keep in mind, conservation applies when the system is closed. So it's a closed system where the objects only interact with each other and nothing else. So there are no external forces from the environment surrounding the system involved. And thinking this way enables us to solve problems without worrying about the details of an event. So it really helps simplify problem solving. So in terms of momentum, in the last unit, we learned that energy is conserved. Like energy, momentum is a conserved property of nature. It is not created or destroyed. So when we have that closed system, we will always have the same amount of momentum within that system. So the only way the momentum of a system can change is if momentum is added or taken away by an outside force. To apply this, what we do is we take snapshots of a system just before and after an event. By comparing two snapshots, we can learn a lot. So, imagine you have your pins here, your bowling pins, at one moment, and then the next, a bowling ball is coming in and applying a force and changing the momentum of that system that was previously closed there. So last lesson, we talked about change of momentum and impulse. So impulse is that change to the initial momentum, resulting in a final momentum. So when a net external force acts on an object, it imparts an impulse to the object, changing its momentum. This is exactly the same for a system of objects. So if you have your initial momentum of a system, and then an impulse is applied, so some sort of momentum from outside that system due to an applied force, you would end up with a different final momentum of that system. Now, if there is no net external force on the system, the momentum of the system is conserved. So the initial momentum would be equal to the final momentum of the system. You've probably seen these before, a Newton's cradle. This demonstrates conservation of momentum. So we would consider that this is a closed system here. Your initial momentum is equal to the final momentum of the system. So all of these together, what is happening here is this first ball here, when it moves and then hits the middle balls, you're actually transferring an impulse, the momentum there, through the other ones to the end. And since the one at the end doesn't have another ball to hit, you see it move. And then it just swings right back and it continues on and on. So in this case, this closed system here, the initial momentum of the system is going to be the same as the final momentum of the system. Okay, so the practice problems that go with this lesson are chapter problems 32 to 34 and multiple choice problems numbers 1 to 10, and you can find those on Google Classroom.